some students watching this video might not see the problem. And the problem is not the numbers, it is the units. If we don't take care of units right now, then we are about to get the wrong answer for the value of delta G. So what do I mean by units? Well, 77 kilojoules per mole of reaction, 121 joules per Kelvin mole of reaction. So these units don't match. I'm going to convert the joules into kilojoules. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 9.1 to 9.3. As you can see on this slide, these topics fall under Unit 9 in the AP Chemistry curriculum, Thermodynamics and Electrochemistry. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now, let's move on to the review for Topic 9.1, Introduction to Entropy. Here are some essential knowledge statements from the AP Chemistry course and exam description. Entropy increases when matter becomes more dispersed. For example, the phase change from solid to liquid or from liquid to gas results in a dispersal of matter as the individual particles become freer to move and generally occupy a larger volume. Similarly, for a gas, the entropy increases when there is an increase in volume at constant temperature and the gas molecules are able to move within a larger space. And for reactions involving gas phase, reactants, or products, the entropy generally increases when the total number of moles of gas phase products is greater than the total number of moles of gas phase reactants. Entropy increases when energy is dispersed. According to the kinetic molecular theory, or KMT, the distribution of kinetic energy among the particles of a gas broadens as the temperature increases. As a result, the entropy of the system increases with an increase in temperature. All right, now it's time to move on to the practice for topic 9.1. This is question 1. In question 1, we are given 4 balanced chemical equations, and the question asks, which of the following equations represents a process that has the most negative value of delta S? So delta S represents the change in entropy, so we're looking for the most negative value of delta S, or the most significant decrease in entropy. Now, starting with choice A, just looking at the phases of matter and the number of moles of each substance on the left side and the right side of the equation, we can see in choice A, I have 2 moles of gas, and they're changing into 1 mole of solid. And with choice B, I see 1 mole of liquid changing into 1 mole of solid. In choice C, we have 2 moles of gas changing into 2 moles of gas. And then finally in choice D, I see 2 moles of aqueous substances. And then on the right side of the equation, I see 1 mole of liquid and 1 mole of an aqueous substance. Now again, we're looking for the most negative value of delta S, or the most significant decrease in entropy. Just to remind you that entropy increases when matter becomes more dispersed, so therefore, in general, changing from a solid to a liquid to a gas would result in increasing entropy. That means that in the opposite direction, changing from a gas to a liquid or a liquid to a solid, that would result in a decrease in entropy. And then we can also see that the entropy generally increases when the total number of moles of gas phase products is greater than the total number of moles of gas phase reactants. So the decrease in entropy would be a decrease in the number of moles of gaseous substances as we change from the reactants to the products. So we are focusing on a decrease in entropy in question 1. So a negative value of delta S that could involve changing from a gas to a liquid to a solid, or a decrease in the number of moles of gaseous substances. I'm going to start with choice C. I don't see a significant change in either the number of moles of gas, and we're not changing phase. So 2 moles of gas changing to 2 moles of gas, that would not result in a significant decrease in entropy. So we can eliminate choice C. And then similarly, in choice D, I see 2 moles of aqueous substances, and on the right side of the equation, we have 1 mole of liquid and 1 mole of aqueous. That is not a significant change in terms of the phase of matter, and there are no gases present at all. We can safely eliminate choices C and D because there would not be a significant decrease in entropy. Now, let's go ahead and analyze choices A and B. They both would involve a decrease in entropy. So in choice B, we are changing from a liquid to a solid. That's 1 mole of liquid to 1 mole of solid. And then take a look at the details of choice A. That's an equation that starts with 2 moles of gas, and then it ends with 1 mole of solid. So as you probably already know, based on the distance between the particles of a gas compared to the distance between the particles of a liquid or a solid, gas particles are far more dispersed. They have more microstates, they have a greater number of arrangements than condensed phases, such as liquids or solids. So therefore, the change from a gas to a solid involves a greater decrease in entropy as compared to the change from a liquid to a solid. And so that makes choice A the most significant decrease in entropy, the most negative value of delta S. So the correct answer to question 1 is choice A. All right, now let's go ahead and take a look at question 2. In question 2, it says the reaction of solid phosphorus, P4, with gaseous oxygen, O2, to form solid tetraphosphorus decaoxide, P4O10, is represented by the equation shown below. So we can see a balanced chemical equation, and the delta S, or the change in entropy, is a negative number. So we know that entropy is decreasing. But what we have to do in question 2 is use particle level reasoning to explain why the entropy decreases as the reaction progresses. Now, on the AP Chemistry free response section, you need to invoke particle level reasoning when discussing changes in entropy. It would not be sufficient to simply say we're changing from a gas to a solid, or if you said gases have greater entropy than solids. That's not particle level reasoning or particle level explanations. So particle level language would include discussing the dispersal of the particles. And you might say number of arrangements or number of microstates. Again, the dispersal of the actual particles themselves, and not simply referring to the phase of matter, such as solid or liquid or gas. So this is what I said in my explanation for question 2. Gas particles are more dispersed, have more microstates, or you could say a greater number of arrangements than solids. And so in this reaction, the entropy decreases because the reactants, which include a gas, are converted into a solid product. So this answer to question 2 is the type of answer that you would need to provide if you saw a similar question on the AP Chemistry free response section involving a change in entropy for a reaction. Now, when we get to question 3, there's going to be a similar style of reasoning, and you'll see that I use a similar phrase of microstates, and I talk about the particles. So let's go ahead and move on to question 3. In question 3, it says, the absolute molar entropy of solid silicon is 18 joules per Kelvin mole. Do you predict that the value of the absolute molar entropy for gaseous hydrogen should be less than or greater than 18 joules per Kelvin mole? justify your answer. So again, as I had mentioned in question 2, you cannot simply say, well, hydrogen is a gas and silicon is a solid, and gases have more entropy. That's not particle level reasoning or referring to the behavior of the particles, especially phrases such as the dispersal of the particles, the number of arrangements, the number of microstates. So take a look at my answer to question 3, and you'll see that I used a similar type of phrase that I had mentioned in question 2, talking about the particles. So this is what I said for question 3. Well, the value of the absolute molar entropy for gaseous hydrogen should be greater than 18 joules per Kelvin mole. The hydrogen or the gaseous hydrogen molecules are more dispersed, have more microstates, or they have a greater number of arrangements than the solid silicon atoms. So the solid silicon atoms are in fixed positions and are less dispersed, have fewer microstates or a fewer number of arrangements. So therefore, gaseous hydrogen should have a higher absolute molar entropy than solid silicon. So if you take a look at my answers to questions 2 and 3 in this packet, this is good advice for how you should phrase your response on the AP Chemistry free response section if you are asked to describe or explain what's happening in terms of the entropy changing for a chemical reaction or a certain process, or when you're comparing the entropy of two different substances. Always talk about the dispersal of the particles, the number of arrangements, the number of microstates, but do not merely refer to the phase of matter. You have to talk about the behavior of the particles when you are talking about entropy on the AP Chemistry free response section. All right, well, hopefully my answers and explanations to questions 2 and 3 make sense and that you understand that advice. Now, we have one more example for topic 9.1. This is question 4. It is a multiple choice question, and we can see it involves particulate diagrams. Question 4 asks, which of the following particulate diagrams represents the change with the greatest positive value of delta S? So question 4 is sort of the opposite of what we had seen in question 1 in this packet. So back in question 1, we were looking for the greatest negative value of delta S. But now we're looking for the change with the greatest positive value of delta S. So we're looking for an increase in entropy. And that might be changing from a solid to a liquid or a liquid to a gas, or increasing entropy might involve an increase in the number of moles of gaseous substances as we change from the reactants to the products. I'm going to begin with choice B. Now in choice B, I can see 6 gas particles in the first box, and then I can see all solid in the second box. So changing from a gas to a solid, that would actually involve a decrease in entropy, so not an increase. So let's go ahead and eliminate choice B. And now I will move on to choice D. I can see 6 gaseous particles in the first box, but I also see 6 gaseous particles in the second box. So we are changing from a gas to a gas, but there is no change in the number of gaseous particles. So that would not involve a significant increase in entropy. Let's go ahead and eliminate choice D. Now in choice C, I do see changing from a gas to a gas. And in choice A, I also see changing from a gas to a gas. Let's focus on the number of gaseous particles. So in choice C, the number of gas particles is decreasing from 6 to 4. That would not involve an increase in entropy. That would not involve an increase in the number of microstates or the number of arrangements. So if I eliminate choice C, then you can see why choice A is the correct answer to question 4. We're looking for an increase in entropy, and we are changing from 3 gaseous particles to 6 gaseous particles. So increasing the number of moles of gaseous particles, that would result in an increase in entropy. Choices B, C, and D all involve a decrease in entropy. So choice A is the correct answer to question 4. Hopefully that makes sense, because now it is time to move on to the review for our next topic. This is topic 9.2, absolute entropy and entropy change. Here is a relatively brief essential knowledge statement from the AP Chemistry course and exam description. The entropy change for a process can be calculated from the absolute entropies of the species involved before and after the process occurs. So if you are given a table on the AP Chemistry exam with values for the absolute molar entropy of various substances, then you would use the following equation. The sum of all of the absolute molar entropies for the products minus the sum of all of the absolute molar entropies for the reactants, that will give you the value of delta S for the reaction represented by that particular equation that you are given. And you can see on the AP Chemistry Equations and Constant sheet in the section entitled Thermodynamics and Electrochemistry, there is that equation for delta S involving products minus reactants. All right, now it's time to move on to the practice for topic 9.2. This is question 5. In question 5, we have to perform a calculation. It says, the values of the standard molar entropies of 3 different substances are listed in the table above. So we can see CH3OH, which is called methanol. We can see CO, which is carbon monoxide, and H2, hydrogen. A student was asked to use the data in the table to calculate the value of the standard entropy change, delta S, for the reaction represented by the following equation. So in the equation, we can see that the methanol is the reactant, and the carbon monoxide and the hydrogen are the products. Now, the student's setup for the calculation is shown below. So what the student did is 198, which is the absolute molar entropy for carbon monoxide, plus 131, which is the absolute molar entropy for hydrogen, minus 240, which is the absolute molar entropy for methanol. And the student obtained a value for delta S of positive 89 with units of joules per Kelvin mole of reaction. Now, we know that there was a mistake because it says identify the error in the student's setup for this calculation and calculate the correct value of the delta S for the reaction. Include units in your answer. So if you haven't found the student's mistake yet, you're about to see what the student did wrong. So there's our equation for calculating the delta S if we are given a table with absolute molar entropy values. So the product, I'm going to focus on carbon monoxide first. That's 198, and the units are joules per Kelvin mole. Here comes the student's mistake. Notice that in this equation, there is a coefficient of 2 next to the hydrogen. So if 131 is the absolute molar entropy for hydrogen with units of joules per Kelvin mole, well, what if you have 2 moles of hydrogen gas? Then you would need to multiply that value by 2. So that is the mistake that the student made in their setup for this calculation. The student neglected to use the coefficient, in other words, ignoring the stoichiometry from that balanced chemical equation. Now, let's go ahead and finish this calculation. We've taken care of the products. Let's focus on the reactant. So the gaseous methanol has an absolute molar entropy of 240. So that would be products minus reactants. And when we finish this calculation, we are not going to get positive 89 like the student got. Instead, we get a value of positive 220 with units of joules per Kelvin mole of reaction. So as you can see, the student neglected to use the coefficient of 2 for the hydrogen gas in their calculation. So on the AP Chemistry exam, if you have to do a similar problem to this one, where you have to calculate the delta S from a table of given values for absolute molar entropy, remember to use the coefficients from the balanced equation in the setup for your calculation. So we have now answered question 5. Identify the error in the student's setup. The student neglected to use the coefficient of 2 for hydrogen in their calculation. What is the correct value of delta S for this reaction? It is positive 220 with units of joules per Kelvin mole of reaction. All right, well, hopefully the answer to question 5 makes sense. Now, let's take a look at question 6. Now, question 6 will be similar to question 5, in that we will use that same equation involving the delta S of the reaction is equal to the sum of the products minus the sum of the reactants. But what makes question 6 different than question 5 is that question mark that you can see in the table. So it turns out in question 6, we already know the delta S for the reaction, and we need to calculate the value of the absolute standard molar entropy for one of the substances listed in this equation. So it says, according to the information in the table and the chemical equation shown above, calculate the value of the standard molar entropy for SO3, or sulfur trioxide gas, in units of joules per Kelvin mole. So let's go ahead and write down that equation. So delta S for the reaction is equal to the sum of the products minus the sum of the reactants. And for the delta S of the reaction, we already know that that is negative 187.8 joules per Kelvin mole of reaction. So I will put that value on the left side of the equation. Now, the sum of the products. We only have SO3 for the product in this balanced chemical equation. There is a coefficient of 2, but since I don't know what that value is, I'm going to represent the products as 2 times x, since x is an unknown quantity, and that's actually the quantity that we're looking for in question 6. Now, for the reactants, I see 2 times the value for SO2, which is known as 248.2 joules per Kelvin mole. So that's going to be minus 2 times 248.2. And then the other reactant is the oxygen gas, which has a value for its standard molar entropy of 205. So what I have right now is negative 187.8 on the left equals 2x minus 2 times 248.2 plus 205. So when I do that math, I get negative 187.8 on the left, and on the right, I get 2x minus 701.4. Now, this just becomes algebra. All I have to do is solve for x, and I will have the answer to question 6. I'm going to add 701.4 to both sides of this equation, and so now I get that 2x is equal to 513.6. Divide by 2, and the value for the standard molar entropy of sulfur trioxide, SO3, is 256.8, and my units are joules per Kelvin mole. So, that is the answer to question 6, and now it is time to move on to the review for our next topic. This is topic 9.3, Gibbs free energy and thermodynamic favorability. There are many essential knowledge statements from the AP Chemistry course and exam description. Let's get started. The Gibbs free energy change for a chemical process in which all of the reactants and products are present in a standard state as pure substances, as solutions of 1 molar concentration, or as gases at a pressure of 1 atmosphere or 1 bar, is given the symbol delta G with that degree symbol, implying standard conditions. The standard Gibbs free energy change for a chemical or physical process is a measure of thermodynamic favorability. Historically, the term spontaneous has been used to describe processes for which the delta G is negative or less than 0. The phrase thermodynamically favored is preferred instead, so that common misunderstandings equating spontaneous with suddenly or without cause can be avoided. So when the delta G, or the change in free energy, is negative, less than 0 for the process, it is said to be thermodynamically favored. And the standard Gibbs free energy change for a physical or chemical process may also be determined from the standard Gibbs free energy of formation for the reactants and products. So there is the equation. The delta G for the reaction is equal to the sum of the standard Gibbs free energy change of formation for the products minus the sum of the standard Gibbs free energy of formation for the reactants. And you can find this equation on the AP Chemistry Equations and Constant sheet. Our next essential knowledge statement says, in some cases, it is necessary to consider both enthalpy and entropy to determine if a process will be thermodynamically favored. The freezing of water and the dissolution of sodium nitrate are examples of such phenomena. Knowing the values of delta H and delta S for a process at a given temperature allows the value of delta G to be calculated directly, and that would be the equation that looks like this. Delta G equals delta H minus the temperature T times delta S. And you can also find that equation on the AP Chemistry Equations and Constant sheet. Our next essential knowledge statement involves this table. In general, the temperature conditions for a process to be thermodynamically favored, in which delta G is negative, can be predicted from the signs of delta H and delta S, as shown in the table below. So what I'm going to do is break down each row of the table by showing you this equation, delta G equals delta H minus T delta S, and considering the four possibilities. Here is our first possibility. If delta H is negative and delta S is positive, then mathematically the value of delta G would be negative at all temperatures. And so if delta G is negative at all temperatures, then the process is thermodynamically favored at all temperatures. Now, let's consider the next row of this table. What if the sign of delta H is positive and the sign of delta S is negative? Well, mathematically, the value of delta G would be positive at all temperatures. So if delta G is positive at all temperatures, now the process is not thermodynamically favored at any temperature. And the next row of the table involves the following situation. Suppose that the sign of delta H is positive and the sign of delta S is also positive. Well, now we can't say for certain whether the sign of delta G would be always negative or always positive, so it depends on the value of T, the temperature. Now, if the absolute temperature is a large number, then the value of the T delta S would be greater than the value of delta H. And so for that situation, the delta G would be negative if the temperature is large. So it would be thermodynamically favored at high temperatures. On the other hand, if the value of T is small, then the value of delta H will be greater than the value of T delta S, and that would cause delta G to be positive at low temperatures. So favored at high temperatures, not favored at low temperatures. Now, moving on to the last row in this table, suppose that the sign of delta H is negative and the sign of delta S is also negative. Again, here is a situation where we can't say for sure if the sign of delta G would be negative or positive. Again, it depends on the magnitude of the absolute temperature. So if the value of temperature is large, then the absolute value of T delta S will be greater than the absolute value of delta H. So under those conditions, the value of delta G would become positive, so not thermodynamically favored at high temperatures. But on the other hand, if the value of T is small, then the absolute value of delta H will be greater than the absolute value of T delta S. So at low temperatures, the sign of delta G would be negative. So thermodynamically favored at low temperatures, not thermodynamically favored at high temperatures. So my message to you, my advice to you is that on the free response section of the AP Chemistry exam, if you need to justify whether a reaction or a process is thermodynamically favored at either low temperatures or high temperatures, this is the strategy that you should use on the AP Chemistry exam. Write this equation, delta G equals delta H minus T delta S. Talk about the sign of delta H, talk about the sign of delta S, and then show whether the reaction would be thermodynamically favored, as in a negative delta G, under either high temperatures or low temperatures or things like that. So it's very important to use this equation, use the sign of delta H, the sign of delta S in your explanation for thermodynamic favorability on the AP Chemistry exam. And I will show you examples of what I'm talking about in the practice problems for topic 9.3. Now, there are two more brief essential knowledge statements for topic 9.3, and they are the following. In cases where the delta H is negative and the delta S is positive, no calculation of delta G is necessary to determine that the process is thermodynamically favored, as in delta G is negative. That would happen at all temperatures. And on the other hand, in cases where the delta H is positive and the delta S is negative, no calculation of delta G is necessary to determine that the process is thermodynamically unfavored. So again, positive delta G, that would happen at all temperatures. All right, well, this wraps up the review of topic 9.3. Now it's time to move on to the practice for topic 9.3. This is question 7. In question 7, we are given a balanced chemical equation, and we are also given the value of delta H for this reaction, as well as the value of delta S for this reaction. The question says, the reaction represented by the equation shown above is run at both 300 Kelvin and 800 Kelvin. Which one of the following correctly identifies the thermodynamic favorability for the reaction at these two temperatures? Assume that the values of delta H and delta S do not change with temperature. So we need to do the calculations to answer question 7. We need to actually pick up our calculator and solve for the value of delta G at 300 Kelvin as well as the value of delta G at 800 Kelvin. So I will begin with 300 Kelvin. The value of delta H is 77 kilojoules per mole of reaction. The temperature is 300 Kelvin. And the value of delta S is 121 joules per Kelvin mole of reaction. Now I will pause for just a moment. Some students watching this video might not see the problem. And the problem is not the numbers, it is the units. If we don't take care of units right now, then we are about to get the wrong answer for the value of delta G. So what do I mean by units? Well, 77 kilojoules per mole of reaction, 121 joules per Kelvin mole of reaction. So these units don't match. I'm going to convert the joules into kilojoules. And you probably already know that there are 1,000 joules for every 1 kilojoule. So here is my conversion factor to take 121 joules per Kelvin mole of reaction. And here's my conversion factor with 1 kilojoule on top, 1,000 joules on the bottom, which means I will be dividing by 1,000. So 121 divided by 1,000 is 0.121 kilojoules per Kelvin mole of reaction. Now, that problem has been solved. But if students didn't recognize that there was a problem with the units, they would get the incorrect answer for the value of delta G. I will pick up my calculator and I will do the following math. 77 minus the product of 300 times 0.121. And so the answer I get on my calculator is positive 40.7. Now, what does this mean? Does this mean that it's unfavorable or favorable at 300 Kelvin? Well, remember that when the value of delta G is negative, it is said to be thermodynamically favored. So that means that when the value of delta G is positive, it is not thermodynamically favored. So we know that at 300 Kelvin, it is unfavorable or not favored. So the correct answer to question 7 is either choice A or B. Let's go ahead and eliminate choices C and D. Now, let's plug in 800 Kelvin into this equation. So I still have 77 kilojoules per mole of reaction for my delta H. Now I have 800 Kelvin. And remember that in order to get the units to match, I will not be using 121, I will be using 0.121 so I can get units of kilojoules per Kelvin mole of reaction. When I pick up my calculator, it's going to be 77 minus the product of 800 times 0.121. And the number that I get is actually negative. I get negative 19.8. So it is going to be thermodynamically favorable at 800 Kelvin because the sign of delta G is negative at 800 Kelvin. So the correct answer to question 7 is choice B. Unfavorable with a positive delta G at 300 Kelvin, favorable with a negative value of delta G at 800 Kelvin. So for this situation, it's going to be favorable at this higher temperature, unfavorable at this lower temperature. So the correct answer to question 7 is choice B. Now let's move on to question 8. Question 8 says, based on the information shown above, a student was asked to calculate the value of the standard free energy change, or delta G, for the reaction represented by the equation shown above at 298 Kelvin. The student's setup for the calculation is shown below. So we can see what the student did. Delta G equals delta H minus T delta S. So their delta H is negative 264. The temperature is 298. The delta S is negative 278. And so they got a value of 82,600. You probably know what the student did wrong. It says in part A, identify the error in the student's setup for this calculation, because I just talked about this mistake in question 7. We have negative 264 kilojoules per mole of reaction. We have negative 278 joules per Kelvin mole of reaction. So just like I had mentioned in question 7, the problem is the units of delta H in kilojoules don't match the units of delta S in joules. So let's go ahead and solve this problem in the same way that I solved the problem in question 7. So what I'm going to do is take that negative 278 and switch that from joules to kilojoules. So the error in the student's setup for the calculation is that there is an inconsistency with respect to the units of delta H in kilojoules and delta S in joules. And now we're going to fix the problem by converting joules into kilojoules. So I see negative 264 kilojoules per mole of reaction. I'm going to leave that number unchanged. The temperature is 298 Kelvin, so temperature goes here. And then finally, as I mentioned, we're going to convert joules to kilojoules. So instead of negative 278, if I divide by 1,000 to go from joules to kilojoules, then that value becomes negative 0.278 kilojoules per Kelvin mole of reaction. And when I pick up my calculator, I will get negative 264 minus the product of 298 times negative 0.278. So the correct answer for delta G in part B of question 8 is negative 181, and the units are kilojoules per mole of reaction. All right, well, hopefully the answers to parts A and B of question 8 make sense. Now, let's go ahead and take a look at question 9. In question 9, it says, given the signs of delta G and delta S at 298 Kelvin for the reaction represented by the equation shown above, is the sign of delta H for this reaction positive or negative? Justify your answer. So the first thing that we should do to answer question 9 is to write the equation delta G equals delta H minus T delta S. So we're not going to do actual calculations, but we can simply plug in the known values of the sign, and then we can determine whether delta H for this reaction should be positive or negative. So I'm going to start with the sign of delta S. So we are given information that the sign of delta S is positive. And now I'm going to make an assumption, and we'll see if it's true or false. So suppose that the sign of delta H is negative. Now, mathematically, if I have a negative delta H and a positive delta S, then this would cause the value of delta G to be negative at all temperatures. And if I have a negative delta H and a positive delta S, this would be thermodynamically favored with a negative delta G at all temperatures, but that doesn't match the information that we're given. Here in question 9, it says that the value of delta G is actually positive at 298 Kelvin. So what I've just done is I can prove that the value of delta H cannot be negative, so therefore it has to be positive. And this is what I said for my answer for question 9. I said the sign of delta H must be positive. So based on the equation, delta G equals delta H minus T delta S, and the fact that delta S is positive, the only way for the sign of delta G to be positive at 298 Kelvin is if the sign of delta H is positive. And here's an alternate form of my answer to question 9, so take a look at a slight variation in the language. So this is another way that you could answer question 9. Based on the equation delta G equals delta H minus T delta S, and that delta S is positive, if the sign of delta H were negative, then the sign of delta G would be negative at all temperatures, which is not consistent with a positive delta G that we are given here in question 9. So therefore, the sign of delta H must be positive so that the sign of delta G can be positive at 298 Kelvin. So either this answer that I'm showing you on this slide or this answer that I'm showing you on this slide. Again, the only way for delta G to be positive at 298 Kelvin is if the sign of delta H is positive. Now, I'm showing you this detail because on the AP Chemistry exam, on the free response section, this is the strategy that you should use. Write the equation, delta G equals delta H minus T delta S. Talk specifically about the sign of everything that you know, whether that's delta H, delta S, or delta G, and then be very clear with your mathematical arguments for things like positive or negative delta G. So this is my answer to question 9, and now as I move on to question 10 in this packet, you will see that I use a similar strategy involving this equation. Let's go ahead and take a look at question 10. Question 10 is similar to question 9 in that we're not doing actual calculations, but we are focusing on the sign of delta H and delta S to determine thermodynamic favorability. So it says here in question 10, a student makes the claim that the reaction represented by the equation shown above is thermodynamically favorable at high temperatures. Do you agree or disagree with the student's claim? Justify your answer. So let's go ahead and write the equation delta G equals delta H minus T delta S. The sign of delta H is positive. The sign of delta S is negative. So mathematically, the sign of delta G under these conditions must be positive. So remember that a negative delta G would be thermodynamically favorable, but a positive delta G is not thermodynamically favored. And in this case, with a positive delta H and a negative delta S, the sign of delta G will be positive at all temperatures. That means that this reaction is not thermodynamically favored at any temperature. So do we agree or disagree with the student's claim that this will become thermodynamically favorable at high temperatures? No, I would disagree with the student's claim. So with a positive delta H and a negative delta S, the sign of delta G will be positive at all temperatures. So therefore, I disagree with the student's claim because this reaction is not thermodynamically favorable at any temperature. Again, just like I talked about in my strategy for question 9, you can see that I began with writing the equation, delta G equals delta H minus T delta S. I specifically focused on the sign of delta H, the sign of delta S, and then I talked about the sign of delta G being positive at all temperatures. Again, this is very clear and straightforward, and it's a strategy that you should use on the AP Chemistry exam if you have to answer a free response question involving thermodynamic favorability. All right, there's one more question in this packet. Let's go ahead and take a look at question 11, which is a multiple choice question. So here in question 11, we are given a balanced chemical equation. We are given information about the sign of delta H and the sign of delta G at 298 Kelvin. And the question asks, which of the following is true about the reaction represented above? Now, what I'd like to do is talk about the concept of driving forces. And that's because the answer choices, 3 of them anyway, talk about driven by. So driven by enthalpy, driven by entropy. So what exactly do driving forces mean? So take a look at the information on this next slide. A reaction is thermodynamically favored when the sign of delta G for the forward process is negative. An exothermic reaction has a negative delta H. And so a negative delta H can be a driving force. Why? Because a negative delta H would support the negative delta G and the favorability of the reaction. Well, what about the sign of delta S? A reaction in which entropy increases has a positive delta S. A positive delta S can also be a driving force. Why? Because a positive delta S would support a negative delta G and the favorability of the reaction. So the conclusion from the information on this slide is that a negative delta H and a positive delta S are considered to be driving forces. So the driving forces that would support the favorability of the reaction, and therefore a negative delta G, would be a negative delta H and a positive delta S. Now, what do we know about delta H in question 11? Well, the delta H we're given is actually positive. So based on what I taught you on that previous slide, a positive delta H cannot be a driving force. So which answer choices in question 11 can we eliminate, since this enthalpy cannot be a driving force? Well, I can eliminate choice A. It says it is driven by enthalpy only, so that's not true. I can also eliminate choice C, which says it is driven by both enthalpy and entropy. Now, let's remember that a negative delta G indicates that the system or the reaction or the process would be thermodynamically favored with a negative delta G. And what does it say in choice D of question 11? It says it is not thermodynamically favorable, but in fact it is. A negative delta G means it is thermodynamically favorable. Let's go ahead and eliminate choice D. So why is choice B the correct answer to question 11? Remember that entropy generally increases when the total number of moles of gas phase products is greater than the total number of moles of gas phase reactants. So what do we have in this equation? 1 mole of solid, 1 mole of aqueous for the reactants, and for the products we have 1 mole of aqueous, 1 mole of liquid. Ah, there it is. 1 mole of gas is featured on the product side of this equation. So number of moles of gaseous substances is increasing, therefore the entropy is increasing. The delta S is positive, and yes, a positive delta S can be a driving force for this reaction. So the correct answer to question 11 is choice B. This reaction is driven not by enthalpy, so not by delta H, but it's driven by entropy. A positive delta S can be a driving force. All right, well, that is the answer to question 11. It's also the last question in this packet. So now it's time to move on to the part of the lesson where I give you advice to help you avoid common mistakes. So my first piece of advice to give you is if you need more information or more practice problems for topics 9.1 to 9.3, then you can review the information in my video for topics 9.1 to 9.7, and you'll find the link to that video in the video description area. My next piece of advice is what I normally say during this part of the lesson. read the question carefully and make sure you are answering the question that is being asked. Always show your work for your calculations. And with respect to topic 9.1, if you need to explain why the entropy decreases or increases, you should provide a particle level explanation. So, for example, the change in entropy is positive when a solid changes into a liquid. So here is an appropriate particle level explanation for that process. Liquid particles are more dispersed, you could say have a greater number of arrangements or have more microstates as compared to solids. So the entropy increases when a solid changes into a liquid. Suppose you have to explain why the sign of delta S is negative for a reaction in which we start with a total number of moles of reactants that is greater than the total number of moles of products, and I'm specifically referring to moles of gas. So not just moles of anything, but moles of gaseous reactants are 3, moles of gaseous products are 2. So here is an appropriate particle level explanation for why the delta S is negative. The total number of moles of gaseous products is less than the total number of moles of gaseous reactants. But keep going. You have to talk about the particles, and the particle level explanation would include if the number of gas particles decreases as the reaction proceeds, the system will have a smaller number of arrangements or fewer microstates, or the particles are less dispersed, and so that's why the entropy decreases. It's got to be including particle level explanations. Now, I'd like to show you some examples from recent AP Chemistry exam questions. So this first question is from the 2025 AP Chemistry exam, and this was a part of the free response question number 3. So there was a balanced chemical equation involving 1 mole of solid reacting with 5 moles of gas to produce 1 mole of solid. And the question said that the entropy change of the reaction, delta S, is negative, and so the students had to use particle level reasoning to explain why the entropy decreases as the reaction progresses. And what you're seeing on the right side of this slide are the official scoring guidelines answer. Because gas particles are more dispersed, have more microstates than solids, the entropy decreases as the reactants, which include a gas, convert to the solid product. Now what I'd like to show you is from the 2025 Chief Reader Report. So what you're going to see on the right side of the slide is the official scoring guidelines. And then what you're going to see on the left side of this slide are 3 examples of why students did not earn the point for their response. So students who simply said less disorder or more order and did not include a particle level discussion of the reaction species did not earn the point for this question. Students who simply referred to a fewer number of moles of products compared to moles of the reactants, but did not discuss the states of matter, specifically changing from a gas to a solid, did not earn the point. And then students did not earn the point for a response with vague language about gas to solid that actually implies that it was the oxygen experiencing a phase change from a gas to a solid, which is not what's happening in this chemical reaction. So I just wanted to give you examples of student mistakes to help you avoid those types of mistakes on the free response section of the AP Chemistry exam. Now, here's another recent question. This was from the 2024 AP Chemistry exam, and this question involved an explanation of the reaction having a value of delta S that's actually positive, so greater than 0. So what students had to do for this chemical reaction represented by this equation is to explain why the entropy increases as the reaction progresses. Now we can see that there are 3 moles of aqueous substances on the left side of the equation. And on the right side of the equation, we see 1 mole of an aqueous substance. We see 2 moles of a liquid substance, water. But the most important substance that is featured on the right side, on the product side of this equation, is 2 moles of gas. So that's the most significant increase in entropy, changing from aqueous to gas. So that would be an important part of the explanation. So here are the official scoring guidelines from this part of free response question 2 from the 2024 AP Chemistry exam. It said, the entropy change is positive because the aqueous reactants produce, and there it is, 2 moles of gas particles according to the balanced chemical equation. Now, that first sentence is fine, but it's not enough to earn the point because we haven't mentioned the particle level feature of this question. So here's the particle level explanation that is required to earn the point. Gases are far more dispersed or occupy a greater number of microstates, or you could say a greater number of arrangements than condensed phases. So the entropy of the products is greater than that of the reactants. Now, what I'd like to show you on the next slide are examples of student mistakes or misconceptions in which they did not earn the point for this particular question, and this comes from the 2024 Chief Reader Report. So what you can see on the right side of this slide are the official scoring guidelines answer, and on the left side of this slide you can see 5 different examples of explanations for the increase in entropy that did not earn the point. First example, an implication that the gas was formed due to a physical phase change rather than a chemical reaction in which gaseous products are produced. So this was not a phase change, but rather a chemical reaction. The next incorrect explanation is that gases are formed, but without providing a particle level explanation. So it wasn't enough to simply say that gases are formed. Particle level explanation was required to earn the point. The next incorrect explanation, it says the products have more entropy due to the formation of, and they mentioned everything together collectively, liquid, gaseous, and aqueous substances, rather than attributing the increase in entropy solely to the formation of a new gas from condensed phases on the reactant side of the equation. So it was primarily about the formation of the gaseous products that was the most significant thing to mention in the response. Another example of an incorrect explanation is that focusing primarily on just the number of moles. So saying that because there are more total moles of product and that's why the entropy increases, that explanation did not earn the point. It had to be about the formation of the gaseous substances. That's a significant increase in entropy for this chemical reaction. And then finally, a generic statement that, well, gases are more random, gases are more disordered or chaotic. That is not a particle level explanation. So again, I'm showing you examples of student mistakes to help you avoid making those sorts of mistakes when you are describing a change in entropy on the free response section of the AP Chemistry exam. All right, my next piece of advice for you in terms of topic 9.2, use the following formula to calculate the value of delta S based on the values of standard molar entropy. And as I have mentioned earlier in this lesson, you know that this formula appears on the AP Chemistry equations and constants sheet. And remember to use the coefficients from the balanced equation in the setup for your entropy calculations. Now, with respect to topic 9.3, when setting up a calculation with the equation delta G equals delta H minus T delta S, pay attention to the units. The units of delta G are usually listed as kilojoules per mole of reaction. Similarly, the units of delta H are usually listed with kilojoule per mole of reaction. But what's different is that the units of delta S are usually listed as not kilojoules, but joules per Kelvin mole of reaction. So pay attention to the units so that you don't avoid that inconsistency with kilojoules and joules. Now, if a free response question on the AP Chemistry exam asks you to discuss the conditions that affect the thermodynamic favorability of a reaction, or to identify the driving forces, for example, enthalpy and/or entropy for a reaction, you should provide a clear answer, connect your choice to the relationship between delta G, delta H, and delta S in the equation delta G equals delta H minus T delta S. So what I'm going to do is show you two more examples, one from the 2025 AP Chemistry exam, and then another one from the 2024 AP Chemistry exam. So in this question, the students were told that the entropy change for this reaction, delta S, is negative. And then they were also told that the enthalpy change for the reaction, delta H, is also negative. And then the question is the following. A student claims that the favorability of the reaction is driven by, again, there's those driving forces, driven by enthalpy and not by entropy. So is the student's claim correct? Justify your answer by using the relationship between delta G, delta H, and delta S. So what I taught you early in this lesson is that a negative delta H can be a driving force for a reaction, and a positive delta S can be a driving force. So in this example from the 2025 AP Chemistry exam, we have a negative delta S, which cannot be a driving force, and we have a negative delta H, which can be a driving force. So here is the official scoring guidelines answer. In other words, is the student's claim correct? Yes. Given that the equation is delta G equals delta H minus T delta S, the reaction must have a delta G that is negative to be favorable. That's an important point. You shouldn't take for granted that the delta G is negative and assume that everyone knows that. You should state that explicitly, that after writing the equation for delta G equals delta H minus T delta S, you should say explicitly that delta G should be negative in order to be a favorable reaction. And then it goes on to say, because the reaction is exothermic, delta H is negative, and so, yes, the enthalpy does contribute to favorability and can be a driving force. But on the other hand, delta S is negative, and so therefore entropy does not contribute to favorability. Now, on to the Chief Reader Report, and I'll show you examples of student mistakes or misconceptions for this question. So on the right side of this slide, there's the official scoring guidelines answer. And on the left side of this slide, you can see 4 examples of student responses that did not earn the point for this question. So an incorrect understanding of the criteria for thermodynamic favorability. So it is likely that students did not fully explain what it takes to be thermodynamically favorable, including a negative delta G. Another mistake was incorrect understanding of the mathematical relationship for delta G equals delta H minus T delta S. Another mistake that did not earn the point was a student that said, yes, both a negative delta H and a negative delta S would contribute to the thermodynamic favorability, which again is half correct. Negative delta H, yes. Negative delta S, no. And then finally, some students did never actually answer the prompt. So they simply listed all of the various mathematical relationships from the equation sheet, but they never did actually answer the response. So again, make sure that you read the question carefully and answer the question that is being asked. All right, on to the example from the 2024 AP Chemistry exam about thermodynamic favorability. So in this reaction, which involves 3 moles of aqueous reactants, 1 mole of aqueous product, 2 moles of liquid product, and then again, the 2 moles of gaseous product. So here's what the question said regarding this reaction, this equation. The reaction has a value of delta S greater than 0, so a positive delta S. The student notices that the temperature of the reaction mixture decreases as the reaction takes place and correctly determines that the reaction is endothermic. So we have a positive delta S and we have an endothermic reaction. And so here the student claims that the reaction is thermodynamically favorable at all temperatures because delta S is positive and the reaction is endothermic. So do you agree or disagree with the student's claim? Justify your answer. And so here are the official scoring guidelines for that. Positive delta S, positive delta H because it's endothermic, and this is the answer. I would disagree with the student's claim that the reaction is thermodynamically favorable at all temperatures. And here's why. The reaction is only thermodynamically favorable at a high enough temperature such that the magnitude of T delta S is greater than that of delta H. So again, focusing on the equation, delta G equals delta H minus T delta S. So another option is to say, I disagree because for the reaction to be thermodynamically favorable at all temperatures, where delta G is negative at all temperatures, the reaction must be exothermic. So not endothermic, but exothermic, and have a positive delta S. So the only way a reaction would be thermodynamically favorable at all temperatures would be a negative delta H and a positive delta S. So as you can see on the next slide, we have the official scoring guidelines from the 2024 AP Chemistry exam for this question, and here are 4 examples of what students had said in their responses that did not earn the point for this question. Now the first one is kind of obvious. You were supposed to disagree, but for the reason that there is a positive delta S and a positive delta H, and so it said, actually, the reaction is not thermodynamically favorable at all temperatures, but then they never actually went on to explain why. Disagreeing with the claim, but only talking about delta S or only talking about delta H, you have to talk about both. Agreeing with the claim by incorrectly stating that delta H is negative, but that is not true for an endothermic reaction. And then finally, making an incorrect claim about a negative absolute temperature. So by giving you advice from the 2025 and the 2024 AP Chemistry exam, and by the way, the official scoring guidelines for these 2 AP Chemistry exams for the free response questions, they are listed in the video description area. I'm just trying to give you good advice and help you avoid the type of mistakes that other students have made on these types of questions. Okay, well, now we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 9.4 to 9.7. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.